Let's talk about the method of cylindrical shells for solids of revolution about the x-axis. So just like before, we need our g of y to be continuous and non-negative. And let me draw a picture to help us understand what's going on here. So let me draw a y-axis over here. And let me draw an x-axis over here like this. So this is x and this is y. And let's draw our curve, which will be g of y. So let's say our curve looks like this. This is x equal to g of y. All right. And we are going to be bounded from below by y equal to c. And we're going to be bounded above by y equal to d, like so. And this time we are rotating about the x-axis, so I'm going to put a little loop here like this. So we're going to call the region that we're rotating Q. So let me put a Q in there, and I'm going to shade the region in yellow. Okay. So let's just make sure we understand the situation. We define Q as a region bounded on the right by the graph G of Y. Whoops, I made a little error there. This should be a G of Y, not G of X, because Y is our independent variable. It's bounded on the left by the y-axis. It's bounded from above by y equal to d. It's bounded from below by y equal to c. Then we can write a formula for what our volume is going to be. Our volume is going to be the integral. Just as a quick reminder, we always chop up parallel to the axis of rotation. So we're going to chop it up like this. And our little bit of thickness this time lies on the y-axis. So we're going to have a dy situation, like so. We have to look at what the smallest y value that we have is, which is going to be c. And the largest y value we have is going to be d. And we're going to have a 2 pi my radius this time is going to be given by the y coordinate, and my height is going to be given by the function value, which is g of y. So this is the radius, and g of y is the height. Okay, and dy is a little bit of thickness. Okay, so why don't we look at an example together? Let's take a look at example 3. In example 3, let Q be the region bounded on the right by the graph g of y equal to 2 times the square root of y. So if we think about this, that's the same thing as saying x is equal to 2 times the square root of y, which means we could have x over 2 is equal to square root of y, which means y is equal to x squared over 4. But remember, we don't have the entire parabola. We're only going to have half of the parabola. So we're going to have only values where the x value is non-negative. This is because we're only taking the positive square root of y. So all the numbers here only result in positive x values. So now I'm going to try to sketch a graph of the situation. So we're going to have a y-axis here like this. We're going to have our x-axis over here like this. Our y values are going to range from 0 to 4. So here's 0, here's 1, here's 2, here's 3, here's 4. And our curve is really going to be a kind of flattened out looking, half of a flattened out looking parabola. So it's going to look something like this. Something like that. Okay. I want to label my bounds. So we're bounded from below by y equal to 0 and bounded from above by y equal to 4. So y equal to 4 looks like this line right here. This is y equal to 4. My blue curve was x equal to this 2 times the square root of y. And our axis of rotation is going to be about the x-axis like this. So we're labeling this region that we're rotating Q, and I can shade that in yellow like this. And this picture illustrates our region that we're going to rotate about the x-axis. So because we are using the shell method, we're going to chop up parallel to the axis of rotation. This means that our little bit of thickness here lies on the y-axis. It's a dy type thing. So when I set up my integral is going to be a dy style integral. The smallest y can be is 0. The biggest y can be is 4. The circumference of our circle is going to be 2 pi r. In this case, our r is being played by y. And the height of the cylinder is going to be given by the function value, and that's going to be 2 times the square root of y. Okay. So let me simplify this integral and evaluate it. So the first thing I notice I could do is I could pull out all the constants. So I'll have 2 times 2 is 4, pull out the pi. So we're going to have a 4 pi outside the integral. We're going to go from 0 to 4. We're going to have a y times y to the 1/2 power dy. We can simplify that. That is going to be 4 pi integral from 0 to 4. This will be y to the 3/2 dy. Now I evaluate the antiderivative. I'm going to get 4 pi y to the 5/2 times 2/5. And this is going to go from 0 to 4. Okay. So when I go to evaluate what this is, I can simplify the coefficients. I'm going to get 8 pi over 5. And then I'm going to get a 4 to the 5/2 minus 0. When you want to evaluate this guy, I would do the square root part first and then raise it to the 5th power. So, you could write this as 4 to the 1/2 raised to the 5th power like that. And that's going to give you 2 to the 5th, which is 32. So we end up with 8 pi over 5 times 32, which simplifies to 256 pi divided by 5. I'm going to tack on some units here. This is a volume, so it's going to be units cubed. And let me highlight that final answer for us. Okay. All right, everybody. This is our example for using shells when we rotate about the x-axis. Take care.